Welcome to the start of our final unit for the year, electrochemistry. And in electrochemistry, we're going to learn about how batteries work. We're going to learn about electroplating, charging batteries, all sorts of reactions that involve electrons being transferred from one place to another. Now, way back in chapter 9, we had a lesson on oxidation and reduction. And might do you well to go back and review that worksheet, but we're going to do a little review here. Just recall that oxidation is when the charge on a species increases. And the charge, remember we talked about the charge being called the oxidation number. And that's because we lose electrons, and we said Leo means losing electrons is oxidation. The species that oxidizes is the reducing agent because it gives electrons to the other species to reduce it. So the oxidizing agent gives electrons to the other species. So we'll talk about those as well. Reduction is when the charge or the oxidation number decreases because it's gaining electrons, and we had Ger as gaining electrons is reduction. And remember we said Leo the lion says Ger to help us remember oxidation and reduction. And the species that reduces is the oxidizing agent because it's pulling electrons away from that oxidizing agent and pulling electrons away from that species that's being oxidized and causing it to be oxidized. So it's kind of this push and pull going on at the same time. Our molecular equation for the first kind of reaction is going to be looking at magnesium metal in hydrochloric acid. So this was a single replacement reaction, if you recall. And what we're going to do is start putting in oxidation numbers so that we can keep track of what's gaining and what's losing electrons. Now remember that any element in its elemental state, like magnesium metal, has an oxidation number of 0. In something like HCl, it's going to have, the chlorine is going to be a -1 charge, as the chlorine is always going to be in a compound like this, and the hydrogen is a +1 charge. And in the products, the magnesium gets oxidized to magnesium 2+, the chlorine stays as a -1, and the hydrogen gets reduced from a 1+ to a 0. And that is our overall reaction. Now, one of the things you're going to start doing, I want you to start thinking about, is putting lines, connecting the things that are being oxidized and reduced with these lines. So the magnesium gets oxidized, and change colors. The hydrogen ion, the H+, gets reduced. And it doesn't matter if you put the lines on top or on bottom. I just put one on top, one on bottom to make it a little easy for us. One of the things we're going to do to hopefully simplify things a little bit is to split strong acids like HCl and magnesium chloride and salts like magnesium chloride into their ions, because we have an acid that splits up 100%. We have magnesium chloride that splits up 100%. And it's going to turn out that the two chlorides on either side are aqueous, and those are what we called the spectator ions. So what we're going to do is just bring down the ions, or the species, not all ions, the species that are changing, to show us the oxidation and reduction directly. So the magnesium comes down, and the magnesium is a solid. Let's put the 0 in just to keep track of it. We have 2H+, that's aqueous, and that's going to be reacting to form magnesium 2+, which is aqueous, and H2 gas, which is in the 0 state. And the way I've written this is balanced. Notice that we have to balance both mass and charge. And we're going to talk about how to use balancing charge to balance equations in a few moments. In number 2, we're going to take a look at an unbalanced equation, and this is going to be essentially the reaction we did at the very beginning of the year when we put the aluminum foil into the copper. It was copper chloride then. Copper nitrate is okay. We can use any copper species, any copper 2+ compound that's going to do this. So what do we have going on here? The aluminum starts off in the 0 state, and on the right side, the aluminum goes into the 3+ state because the nitrate is a -1, and so we need 3+ aluminum to balance out those 3 nitrates. So the aluminum is being oxidized. Meanwhile, let's look at the copper. Copper starts off as a 2+ because it's with the 2 nitrates, and on the product side, the copper has been reduced to a 0, and so we can tie those together and have that as our reduction. And notice, sometimes as in number 1, they overlap each other. Sometimes as in number 2, we have one inside the other. There's no real importance to either way. You can write them either way. You can write the products in either orientation. You can write the reactants in either orientation. In this reaction, the nitrate is going to be our spectator ion. We have total of, we'll talk about the balancing in a few minutes. We recognize that the nitrate's going to be the spectator ion because it doesn't change charge. So in this case, the spectator does not change. And so that's going to be an important observation as well. So when we bring down our remaining species, we're going to have aluminum plus Cu2+, that's aqueous, is going to form copper 0 as the solid, and aluminum 3+, and that's aqueous. So this is really the reaction that's going on. One is being oxidized by the other is being reduced by the first one. And so what we're going to do is separate these into what we call the half reactions. And these half reactions you're going to find on chart H. And we'll get more into those as we get into this lesson and tomorrow's lesson. So the oxidation half reaction started with aluminum. And for now, I'm going to omit the states just because it's going to be a little messy if I put the states in. So we're going to start off with the aluminum, and that's in the 0 state. You don't always have to write the 0 in, and in fact, I'm going to start omitting it as well. When we react, we made aluminum 3+. Now, I said that we had to balance mass and charge. So in order to balance charge, the only thing that I can do is use electrons to balance the charge. And so what I need to do is put electrons either to cancel out an excess positive charge or to match an excess negative charge. In this case, we have 3 aluminum 3+ in the product. So in the reactants, I have a total of 0. In the products, I have a total of 3+. So I need to balance that with electrons, and I'm going to balance that using 3 electrons. These half reactions will always use electrons. You'll always see these electrons in the half reactions. Meanwhile, we've got the reduction to take care of. In the reduction, we have copper 2+. And as I think I said back in chapter 9, when we talk about what the particular species is, it's important to say the correct charge. Because if you say that copper is being reduced, I'm going to think copper in the 0 state, and that's not going to work out. All right, I'm going to leave you a little room here, and you'll see why in a moment. And we're going to make copper, copper 0, and that's going to be our solid. And now to balance the charge, I'm going to have to put 2 electrons in the reactants. And so in the reduction, we always have the electrons going in. In the oxidation, the electrons are always coming out. Now, we can balance this by balancing electrons. So first we balance each individual reaction with electrons, and then the next thing we do is we want to equalize the number of electrons in both reactions. And we want to do that because in the end, in the balanced net ionic equation, we cannot have electrons in there. So since we have 2 electrons in the reduction and 3 electrons in the oxidation, what we have to do to balance those out is use our least common multiple, which is going to be 6. So we're going to multiply the first one by 2. We're going to multiply the reduction by 3. And what that's going to end up giving us is 2 aluminum plus 3 copper, capital C there, copper 2 plus. Now I'm going to have, let's just put it in for now, the 6 electrons. We'll get rid of those in a moment. I'll show you how this works. On the left side. On the right side, we're going to have 2 aluminum 3 plus 3 copper 0, and we're going to also have 6 electrons. And so we're never going to write those electrons again. The 6 electrons on both sides cancel out, and they leave us with the balanced net ionic equation. In that, as I said before, mass balances, and you can check that mass balances. 2 aluminums on the left, 2 aluminums on the right, 3 coppers on the left, 3 coppers on the right. Mass balances, good. And charge balances. Now, the charge doesn't have to equal 0. It just has to balance. And it turns out we have a 6 plus on left side, 6 plus on the right side. And so it balances out. So this is the reaction that took place when we put aluminum into a solution of copper 2. If the reverse reaction had taken place, we'd basically have this back and forth going on where the copper metal could now reduce the aluminum. But that reaction does not occur. So the copper metal trying to reduce the aluminum gives us no reaction. And we talked about that last time in terms of where the particular materials are on the electrochemical series on chart H, and we will get more into that right now. But for now, there's also going to be some important stuff that we're going to talk about, which is noting that this is the reaction that occurs. So this is the spontaneous reaction, which means that this spontaneous reaction is the one that has the negative delta G. There are equilibrium constants associated with these, but we're not going to get into those. The reason has to do with the ability of one thing to remove electrons from another better than the other way around. In other words, something is easier to oxidize, something is easier to reduce. And in this case, the aluminum is easier to oxidize than the copper. So aluminum was easier to oxidize than copper. You can also say that copper 2 plus is easier to reduce than aluminum 3 plus. And we'll talk more about that and put some numbers on all of this tomorrow. Now let's talk about what's going on in solution when these reactions take place. So here is our beaker, and in the beaker we have some solid aluminum. So this is our solid aluminum here. And we have our aqueous copper, 2 plus. And what happens is each aluminum has 3 valence electrons. So let's put in those 3 valence electrons. And those 3 valence electrons get transferred over to the copper 2 plus. So 2 from that aluminum go to 1 copper. We have 2 from those 2 aluminums come to this copper, and 2 from that aluminum come to this copper. So we're transferring those electrons, and what we're making in the process is aluminum 3 plus. And I think I'm going to have to change colors, otherwise you're not going to see it. Aluminum 3 plus, and I've got 3 coppers, that those 3 coppers have now attached to the solid. So the copper becomes solid, and the aluminum 3 plus comes out of the crystal. It comes out of the metal crystal and becomes the aqueous aluminum 3 plus ions. Notice that the reverse reaction is never going to occur, and this is what I mean. So copper is never going to give, it has those 2 electrons, it's never going to give those electrons to aluminum because it's not easy, it doesn't have enough power to reduce that aluminum. Okay, so that's what we need to know for now. And this reaction is exciting, right? It was a lot of bubbling and boiling, and it got hot, and it steamed, and we went ooh and ah, and that was great. But for all the bubbling and boiling, we couldn't do anything with those electrons. And wouldn't it be great if we could figure out a way to harness those electrons so that as they transfer from the aluminum to the copper, we had the ability to, say, run a phone or run a computer or run a flashlight or any of many different kinds of applications that require electricity. So that's what we're going to do. We're going to find a way to get those electrons to do work for us. And we're going to do that by creating what's called a voltaic or a galvanic electrochemical cell. In a voltaic or galvanic, and I'm going to stick with voltaic now because that's the most common usage, we use a spontaneous redox reaction. So in the spontaneous redox reaction, the delta G is going to be less than 0, and that's going to generate electricity. And what we're going to do is force those electrons to flow in an external circuit, like your computer or like a flashlight, rather than directly from one reactant to the other. And we're going to do that by taking the 2 half reactions and splitting them into what we call half cells. And a half cell, I'll describe down below, I'll show you down below, but the half cell contains both the oxidized and the reduced form of the species from the half reaction. So let's look down below, and you'll see on the left side, I have a cell that has aluminum in it and aluminum 3 plus. And this time and some nitrate in there. The nitrate, again, that nitrate is just there because we need to balance charge. You can't have aluminum 3 plus in solution without some nitrate. Now, in this beaker, this is where our oxidation is going to take place, where the aluminum is going to get oxidized to aluminum 3 plus, and we're going to produce 3 electrons for each aluminum that does that. On the right side, we have copper and copper 2 plus, and here we're going to take the copper 2 plus and we're going to add 2 electrons for each copper 2 plus, and we're going to create copper metal. All right, so what reaction happens, as we said up above, is exactly the same as a single replacement reaction. In fact, all batteries are based on some sort of reaction like this. And what's going to happen is instead of transferring from the aluminum into the copper 2 plus through the solution, we're going to oxidize the aluminum and we're going to have electrons flow to the copper 2 plus. So here's what's going to happen. Let's write an electron in here. So we've got an electron. We're going to need 3 electrons, but eventually we'll have those 3 electrons. So the electrons are going to transfer the only way they can. They're going to go up through the aluminum. They're going to go through the wire. This is a voltmeter. This could also be a flashlight, a light, or something else. And so the electrons are going to transfer. You're going to draw the electrons transferring from one electrode. The metal is called the electrode. So this has an aluminum electrode and a copper electrode. And we're going to get those electrons to come down into the copper, And when they do, what's going to happen is the electron then is going to be able to transfer to the copper 2 plus. And when it does so, the copper 2 plus is going to come onto the copper electrode. On the other side, because we're losing electrons, we're going to take the aluminum that's there and we're going to form aluminum 3 plus in that cell on the left. Now, these cells have some names that we have to know about. In this particular case, and it's not always going to be the case, on the left we have what's called the anode. Now, you may have heard these terms before. The anode is where the oxidation takes place. And we have a little mnemonic for you. The anode is the mnemonic, another animal mnemonic, anox. So anode is the oxidation. On the right side, we have the cathode. The cathode is where the reduction takes place, and this is going to always be true. And our mnemonic for the cathode is a red cat. So not only do we have Leo the lion says grr, we have an ox and a red cat. In these electrochemical cells, the electrons always flow from the anode, because they're going from the oxidation to the cathode, to the reduction. And hopefully that makes sense to you. All right, so there's some more things going on here. The anode is always given the negative charge. So this would be the negative pole of a battery. So if this was a battery, this would have the negative. The cathode is always the positive, because look what's happening. Positive is attracting electrons. Okay, and the negative is the source of electrons. So negative sources the electrons, the positive attracts the electrons. Source of electrons. Now, there's another thing going on here that we need to talk about, and that is this thing in the middle with the sodium and the nitrate in it. That's another solution that bridges between one side and the other. In fact, this is called a salt bridge. What is the salt bridge needed for? Well, let's talk about what would happen if we didn't have the salt bridge. In the anode, as we lost those electrons, the anode would build positive charge. The anode builds positive charge. The cathode, gaining the electrons, is going to build negative charge. And when that happens, what ends up happening at first is the electrons can no longer flow, because if we're building a positive charge, that's going to attract the electrons, and the negative charge is going to repel the electrons, and it's going to stop the flow of electrons. So we need something there that's going to continue the flow of electrons, or continue the flow of current. Now, the only place electrons can go is in the wire. Electrons can't flow through the solution, so we can't have anything coming from one side or the other. In the single replacement reaction, I kind of drew it incorrectly, if you'll forgive me, on the front page, in that the aluminum and the copper 2+ actually have to come in contact for that transfer to take place. So what happens in the salt bridge is three things. Number one, we get ionic conduction. So what we're going to do is use ions to go between the two half cells. So we get ionic conduction. And in this case, the positive sodium is going to go to where the negative charge is building up. So the positive sodium is going to move to the right. The negative nitrate is going to move to the left in the direction towards the positive buildup of charge. So this is where we get the attraction that prevents the buildup of charge. So then that's the next thing. The conduction happens, and it neutralizes the charge that would build up. And the other thing it does is just something you always need, is that it completes the circuit. We always need to have a complete circuit. We need to have a complete circle going on here. And one way to remember the direction that these go is if we look at this as a clockwise versus counterclockwise circulation, the negative charge is always going to go to the, in this case, the clockwise direction. Now, it's going to be the opposite if the cathode is on the left. Let me redo that so it looks like a negative charge. Negative charge is going clockwise. So you see in the wire up above, the electrons are flowing to the right. In the salt bridge down below, the negative electrons are flowing to the left, and the positive cations are flowing in the opposite direction. So they always go in opposite directions, and hopefully that makes sense to you. A couple of more things, and we will be done. You notice that in the electrodes, the aluminum is coming out of the electrode. So the aluminum becomes the aluminum 3+, and that aluminum 3+ is what dissolves. Please don't say the aluminum dissolves. The aluminum becomes aluminum 3+, and it dissolves. Because it dissolves, the aluminum is going to lose mass. And the anode, because it's the oxidation, the anode will always lose mass. And at our lab next week, we're going to talk about that. Always loses mass. On the right-hand side, the copper gets reduced and forms copper metal. And that copper metal, as I said, plates out. Copper, we call it plating out. Plates out. It attaches, plates out onto the copper electrode. And so the electrode in the cathode always gains mass. All right, so the cathode gains mass. And that's basically it for the setting up of these guys. Let me just note on what I said here. This is without the salt bridge. So you don't think this is happening if we have the salt bridge in place. Again, this is without the salt bridge. So in tonight's homework, you'll have some questions that are going to be about putting these together. Oh, we know that the direction of flow is from the aluminum, the electrons going from the aluminum to the copper 2+, because that's the direction of flow that we saw spontaneously as a single replacement reaction. So that's going to be a clue to tell you when I give you your electrochemical cells, your voltaic cells to set up, what direction we're going to have the flow of electrons going. I am going to post, it's the best video that I could find, a video in which they're going to describe and show you the making of an electrochemical voltaic cell using copper 2+ and zinc. I didn't want to use zinc in this lesson because zinc is a 2+, copper is a 2+, and you wouldn't see how to balance out electrons. Now you know how to do the balancing of electrons. All right, so I hope you have a good rest of your day and do well with the homework. I'll see you next time in class.